Welcome to this presentation on C++ pointers. For some of you this may be a review, but I think there's some maybe new information, interesting information in some of this for you. So we'll start off with Visual Studio and just do a quick review. In Visual Studio you can't just open a source file and start working. You have to work in the context of a project. So when you start the newest version of Visual Studio, you get this, and you can continue without any code, or you can create a new project. Some of the previous versions of Visual Studio, you would start and maybe get a window that looks like this. To create a program, you have to begin with a project or a solution. You can't just open a C++ file and start working and expect it to build and run. So to create a project or solution, you go to the main menu and File, New Project. And this looks a little bit different depending on which version of Visual Studio you're working with, but we want to create a C++ console application. And you'll hit Next, and in some cases you'll want to choose an empty project or a project that doesn't have any source code in it already for you. And the location is important too. You want to be able to find it easily later, so you want to put this in a location that's easy to find. So I just happen to have a CEIS 295 folder, and I'll call this project pointer test or something like that. And a lot of times there's an option for having the solution and project folders share the same directory, and I find that useful with simple programs because it makes things a little bit less complicated. Instead of having two folders, the one parent and child with the same name, you just have a single folder, and it seems to be a little bit simpler sometimes. So when you create, depending on the project settings and which version of Visual Studio, you might get some source code, you might just get something empty where you would have to add a new C++ source code item and start creating code. And notice that the location will be in that folder that we chose with the project or solution name appended to the end of it. Here we already have some source code, and I'm going to maybe get rid of most of this, most of these comments. And it just says hello world. I like to put the using namespace standard here so that I don't have to put std in front of everything. And we're ready to start. What I'd like to do is review the concept of addresses and pointers and storing and accessing things through addresses and pointers. So let's start with creating a simple integer x equals 7. And very often when I program with data structures, I find it very useful to create little diagrams. So I've been doing this for a long time, decades, and even today when I work with data structures, it's very common for me to have a piece of paper on the side where I'm creating little diagrams of what pointers point to what when, and we'll see more and more examples of this as we go through the course. But here with this example, what I'll do is create just a text box here, and in this box there'll be a value, an integer value, which is 7. And I'll also create another, let me see if I can get the box to show up. Okay, so now the box shows up, and this box has a name, and the variable name for this is x. So that's what this diagram might look like for now. I have a storage location for a single integer, its variable name is x and its value is 7. And of course we know we can print this out and it'll just print out a 7 on the output. What I want to show you is how we could also access this storage location through its address or a pointer. And the way you do that in C++ and in other languages use references for a similar thing, and the syntax with pointers in C++ is a little bit different, a little bit more cumbersome, but it's very similar to the concept of references in other languages. So we can create an integer pointer p, and set that equal to the address of x. So this declares a data type that is an integer pointer. So x is an integer and p is an integer pointer. So in our diagram then, I'm going to create another box. And it's p. And what value goes in the box for p? And that's a little bit tricky to answer because we don't get to choose where variables and items are stored in memory. So this variable x is stored somewhere in memory, but we don't get to choose it. We don't know what its address is. So instead of putting in some kind of an address, what we normally do is to draw an arrow from p to x. So we say that p refers to or p points to x. And that's the way this situation works. We can look up the address at a particular time when the program is running by using the debugger. So if I set a breakpoint here, and for those of you that haven't done debugging, a breakpoint is just a line in the program where the program will pause during debugging, and we run it in debug mode, start debugging, and it needs to build or compile first. Hopefully there won't be any errors. And so it's running, and you can see we don't have any output yet because the cout statement has not executed. And you can see this yellow arrow indicates the line where the program is paused. And down here in the watch windows, we can look at values of particular variables. So in particular, the variable x has a value of 7, and the variable p has a value of this big hexadecimal number, which is the address of the variable x. And you see that it's showing us the address, and it also showing you what that address is referring to. Every time you run this program, you may get a different address because your program may be loaded in a different place in memory. And in general, we can't predict what that value is. So in our diagrams, when we work with pointers, instead of putting a value in here, we put an arrow of what it's pointing to. And if it's not pointing to anything, or it's uninitialized, we may put a question mark in there so we know that we don't know what it's referring to. Or if we initialize the pointer value to 0 or null, we may put a null text in there to represent that it's not pointing to anything right now. So that's the basics of pointers and addresses, at least setting up a pointer and having it refer to an address. If we want to access the location that a pointer is referring to, we use this dereference operator, which is *p. So these two cout statements will do the exact same thing. They'll print out the value of 7, but they have a little bit different way of doing it. The one way is we access the variable x directly. The other way, we access the variable x indirectly through the pointer p. And so the asterisk to the left of a pointer is what they call the dereference operator, and it dereferences the pointer or follows the arrow to get us access to what's inside the box for x. So this is a little bit confusing in C++ in that the asterisk operator has at least 3 different meanings for us now. The original meaning we may have seen is for multiplication. Another meaning when it's used to the right of the data types means that we're declaring a pointer data type. And then when it's on the left of a pointer value, it means to dereference that pointer or follow the arrow and access its value. We can also use pointers to allocate new values. So instead of having p point to the address of x, I can create a new integer and optionally give it an initial value of 12. And now when I run this, I should get 7 and 12 printed out. And we'll have a slightly different situation in our diagram where copied too many things here. I've got another integer variable whose value is 12, and p is going to point to or refer to it. So I have this situation. So now in the code I have the variable x as a value of 7. I've got another integer variable which interestingly does not have a name. So variables in blocks of memory that you allocate with new don't have variable names. P is a pointer variable, an integer pointer, and it can point to this unnamed integer that has the value 12, but it could also point to something else. And this brings up a potential problem that can occur. When we're finished with allocated memory, unlike other languages like Python and C# and so on, C++ does not have a garbage collector or a memory manager like the other languages do. So if we allocate memory with new, it's important that we free up that memory. And in this case, the way we do it is with the delete command. So we delete that memory without the brackets, just delete p. So when we're finished with that block of memory, we delete it. If we were to fail to delete this, and this code that allocated somehow were inside of a loop, then what would happen is we would allocate another block of memory. In this case, it's just 4 bytes for an integer, I guess. And p would point to that, and maybe it would have the same value, maybe a different value. That's not important. But what is important is that this old block of memory now doesn't have a name and doesn't have a pointer referring to it, and so we've lost access to it, but it's still reserved and taking up space in our program. And this is referred to as a memory leak, and if that loop executes enough times, it will continue to allocate, and not free up memory, and this can cause your program's performance to degrade and eventually cause the system to crash if you try to allocate so much memory and not free it up. So this is a good lesson in C++. You have to do your own memory management, your own deallocation, which is a good lesson to learn. And you want to try to avoid memory leaks like this. Something else that's interesting is that there's a relationship between arrays in C++, and pointers. So if I declare an array and give it some initial values, I can set p equal to the address of the first element in the array. So now our diagram looks a little bit different here. Where we have 4, maybe a table would be better, but See if I can. So I have an array whose name is A. And the values in the array are 2, 4, 6, and 8. So this is what the diagram looks like now. X is still 7, that hasn't changed. I have an array A with the values 2, 4, 6, 8, and the array has indices 0, 1, 2, 3. And this line here sets the address of A sub 0, so the address of the first integer in the array, equal to or assigned to the pointer P. So P points to the first thing in the array. And now we could access or print out an element in the array by saying cout A sub 2. We can also do the same thing with the pointer. We can cout P sub 2, and that will, both of those lines will print out the 6. So what this indicates is that an array name and a pointer are almost the same thing. The only difference is the array name cannot point to or refer to any other block of memory, but a pointer variable can. So we've seen that P can refer to X, P can refer to the first thing in the array, P can refer to a newly allocated integer, and P can also refer to some other location in the array. Normally you don't do that, but you could. One other thing to keep in mind is that since P does no longer refers to a dynamically allocated block of memory with new, then we don't want to delete P because this is an array that was not allocated with new, so we don't want to delete it. So this line needs to be removed. But interestingly, these two statements print out the same thing. They both print out the third element in the array, which is the value 6. Something else to remember, maybe you've seen this or not, we can create a class or a structure, maybe a rectangle, and we can make everything public, keep things simple, and we could have the rectangle have a width and a height, and we could create maybe a default constructor. For that particular rectangle. And then in the code, we could declare a rectangle and say it has a width of 5 and a height of 3. And we can declare a pointer to a rectangle. And so now our diagram will look a little bit different, where a rectangle R1 has got data members, two different data members, one for a width and one for a height, and the width value is 5 and the height value is 3, and our pointer now is called PR, and it points to that rectangle, and we no longer have our array. And if we wanted to print out the width of the rectangle, we could say r1.width. And if we wanted to print out the height of the rectangle, we could write r1.height, or we could also write, we can access it through the pointer. So we can say PR and then a hyphen greater than, so like kind of like an arrow, height. So this is what they refer to as the pointer indirection or pointer dereference operator. So what we're doing is saying that PR is a pointer to a rectangle. A rectangle has data members for width and height. We can access the width through the original rectangle variable name, or we can access one of the data members through the pointer to the rectangle. And so this should print out width equals 5 and height equals 3. So this is showing you how to access a data member within a class or a structure through a pointer. And we'll start to see this next week. Again, if we wanted to, we could have accessed, or we could have created a rectangle dynamically. So that we don't even need R1. So then this name goes away. It's dynamically allocated, in which case we have to access both the width and the height through the rectangle pointer. And of course, when we're done, we want to delete the rectangle so that we don't potentially cause a memory leak. So the last thing I want to look at in this is the resize operation we saw in our array list. So here's an array, and let's bring up our array list program that we looked at in a different presentation. In the array list class, we have a pointer to data. So I'm going to update my diagram here. And this is really one of the key things I wanted to show you. Is I find these diagrams to be very useful in working with pointers and addresses and data structures. And even today, after doing this for many years, when I program data structures, it's very common that I've got pieces of paper with these diagrams so I can understand how certain algorithms work. So in this case, our pointer, I guess, in the array list class is going to be called pdata. And we may have other pointers as well. In our main here, I'm going to create, take out some of this here. And I'm going to create a list. I'm going to add some things to it. I'm going to add the values that are in the diagram over there. And because and let's see how big the list is going to be. Okay, so the initial capacity of the list is 10. So let me change that so that the initial capacity of the list is 4. So in the constructor of the array list, we get to choose what the initial capacity is. And depending on the application, you might find different values more or less useful. And then as we add items in to the list, if the current size of the list is equal to the capacity, that means the list is full. Then what that means is we're going to resize the list to be twice the capacity and then add the new item to the list. So I'm going to start out with a list size of 4 to try to match the diagram here. And again, this is dynamically allocated data, so it's referred to by a pointer. Pdata. In The main part, I'm going to add the appropriate values, 2468, and just print it out. Our list is my list display. And this code comes from the other presentation we looked at this week. And if we run this, I don't think we'll be surprised that we see my list is 2468. That's what we have in the diagram. What happens when we go to add something else? So I say my list dot add 10. When we do this add, what will happen is that the current size is 4, the capacity was initialized to 4. So this will be true, indicating that the list is full. So we're going to call this resize function. What happens in this resize function, and this is where we're getting to a diagram. In resize function, we have a temporary pointer, ptemp integer pointer that's set equal to pdata. What does that mean? What does that do? What that means is it sets up another pointer variable, and it's called ptemp, and it's going to be equal to the same address that's in pdata, which means it's going to point to the same thing that's pdata is pointing to. So I'll do something like this in my diagram. So once this line is executed in the resize function, ptemp is going to have the same address as pdata, which means they're both going to point to the first element in this list. Now the next thing that happens is capacity gets set to new size, and that new size will be 2 times the original capacity. So new size should be 2 times 4, or 8. What that means is that we're going to get a new block of memory allocated for pdata. It's going to be 8 instead of 4. So I get a new block of memory here that's going to have room for 8 things instead of 4, and that address of that new block of memory gets stored in pdata. So now the diagram needs to be updated, where pdata no longer points to the old array, but pdata points to the new array. And we now have room for more things. Hard to get this to line up really well, I guess. The spacing is a little bit weird on this, but I guess we kind of get the idea. That's a little better. Okay, so now we have room for 8 things in this new block of memory, but the values are not initialized. We haven't put any values in here. So the next step in this resize function is to go from 0 to the current size, and remember, we haven't added the new thing yet, so the current size is still 4. The capacity has been increased to 8, but the current size is still 4. There's only 4 things in the list. So we're going to loop from 0 to 4, 0, 1, 2, 3, and we're going to take the value at ptemp sub 0 and copy it or assign it to pdata sub I. So we're just taking each of these values and copying them over. When I goes to 1, we're copying over the item in the second spot, and then the third spot, and then the last spot. And then we're finished with this loop here. We've copied everything from the old block of data to the new larger block of data. We want to make sure we delete the older block of data that we no longer need anymore. So we do this with this delete with the square brackets, and now this section of code here causes this old block of data to be deleted or freed up so that it can be used somewhere else. So I'll just maybe draw an X through it. It's been deleted or freed up, and we don't have to worry about changing ptemp because it's a local variable here. It's going to be destroyed, so we don't have to worry about setting it to null or anything like that. We finish with the resize, so we're back up here, and now we're going to add in the new item, which was a 10, and we're going to add it at the current size. And remember, the current size is 4, so coincidentally the current size just happens to be the same. The current size also happens to be the location where we want to add the next thing. So the 10 will go here, and then the current size will get incremented to 5. And so again, I find these diagrams to be extremely useful in understanding how different algorithms with data structure work, such as this resize. So I hope you find this useful too, and don't be afraid of drawing out these diagrams on a piece of paper. Write out all your variables as boxes, put the values in the boxes, draw the arrows so you know what pointers are pointing to what, so you can keep track of things and how things are working in your program. And be sure to contact me if you have any questions.